Okay, well, welcome back to the second part of today's medal symposium, medal ceremony. We will start with the Laudatio for Michele Parrinello, which will be given by Giuseppe Foffi. He has been so kind to agree to give the Laudatio, and Giuseppe is a theoretical soft matter physicist working on colloids and glasses. He got his first degree from La Sapienza, and then he moved to Dublin, got a PhD there, moved back to La Sapienza as a postdoc, then worked at the EPFL in Lausanne, and since 2013 or so, I think, he is in University of Paris, Saclay, and today is here, and please, the floor is yours.
Thank you. Okay, so I think I'm on. So it's a pleasure to be here and to introduce the prize for Michele Parrinello. I'm a soft matter physicist, computational physicist. I've never done an atomistic simulation in my life. I've never done a quantum calculation in my life. So why I'm here is that when I moved to EPFL, I was actually in an institute that was called IRMA, that you probably remember very well, and it was actually a postdoc of Alfonso Baldereschi. So. And I got exposed to all the people in the community of the ab initio simulations of Andandreoni. And so I got to know the name of Michele Parrinello, and I started to look. I always look at his work because they were the kind of work that I always find very inspiring, because they were they express a huge curiosity, a great creativity, and something that I will try to communicate with my lecture today. So you already seen these kind of pictures before in the talks today. So we know that in general there is always a problem of length scales in sciences, right? So we all know that physics is the basic of all the sciences, but of course bridging physics to the other branch of sciences is very difficult. And indeed, even if we look inside physics, we have many different length scales. I mean, most of the physics would be probably in a place like here, where you have a quantum description, atomistic, mesoscale, where the different effects of different theories will make them feel. And it's interesting because, in fact, a lot of the time we know a lot about each level, but we don't know how to bridge them together or how to solve them, really. So if you think about classical quantum mechanics, this would be something like one particle, two particles, whether they're quantum or they're classical. We do know the basic equation that govern this kind of system. And also, if we go to large systems, so we start to be interested in condensed matter and the emerging property, when we start to put a lot of particles together, we also know the laws that more or less govern this, at least in equilibrium, and these were the laws that were developed in the field of statistical mechanics. But so this means that, in principle, we could solve the problem, and this was something that was realized by Dirac himself, right? In this famous lecture, he says something like, okay, we can now, if we forget about relativity effect, which is not something that concerns condensed matter, we can assume that everything is Coulombic, right? And so we know everything about electron and atom and the interaction. We can also basically know the theory and the physics behind the wall of chemistry and everything else. So basically what we just need is approximation and methods to do that. And this seems like a finished problem, but in fact it's very difficult, because you know that solving mathematically this kind of problem is in fact very hard. And in fact, even if you do approximation, the more you approximate, the less your theory is really predictive of reality, in a sense, right? If you really want to be exact in a field like chemistry, right? And so this was the 29, and everything changed in the 50. Why? Because people started to develop huge computers, and in this year, the two seminal papers of computational physics were developed. And then from there on, there was a different idea, and one could have asked ourselves what would Boltzmann have done with a computer, right? As this very famous picture from this nice article by Del Lago asked us. So what have we done? So probably one of the things we could do, and we did, was to go back of one of the basic assumptions of statistical mechanics, and this is basically that time averages are equal to ensemble averages. And these two branches of these two equations created the two basic branches of computational physics in molecular simulation. On one side, you have molecular dynamics, in which basically you solve the equation of motion, and then you make time averages. On the other side, you have Monte Carlo simulation, in which you directly attack the problem by knowing that you know a lot about the ensemble averages and the distribution. So today I'm going to talk only about molecular dynamics, because indeed this is the field in which Michele Parrinello has been more impactful. And molecular dynamics in principle is super simple. Basically, you write down the equation of motion, you feed them into a computer, you discretize them, and you solve the problem. And then you have basically a trajectory in time, and you can calculate time averages. But not only that, you also have the dynamics of your system. So in principle, you have the access to the dynamics. So the principle itself is super simple, but there are a lot of key things that you need to know. So first, all of this is in a constant energy surface, right? So you're scanning only the microcanonical ensemble. And this is not really a practical ensemble to compare to real life, because we don't easily prepare a system at a constant energy situation, and we would like to go in different ensembles. The other question is, what do we say about this interaction potential? How do we calculate them? And then also, since it's a dynamic process, you risk to get trapped in certain points in your phase space. And the ergodic hypothesis is an hypothesis. Doesn't mean that your trajectory, if you solve this project, will go ahead. And finally, since you need to have large enough system, you need to anyway bridge whatever is the single atom to the large system. So I will try to guide you to these 3-4 questions, and I'd like to show you how Michele Parrinello impacted in a fundamental way each of these problems that I'm showing you today. So I will not make a story about biography or whatever. I will let really the science speaks, because otherwise I don't even know if I managed to say all I want to say. So the first things I did was really to go to these most cited papers, and indeed I picked those that for me are made really a huge impact, and all of them has been more or less mentioned them, and I will sort of go through them and try to guide you how those papers address those problems that I gave you before. And at the end, if I manage, I also show something very, very recent to show you a bit of new ideas in the dynamics of Monte Carlo. Okay, so the first question is how do you move from a description that is a constant energy description as a standard molecular dynamics to a situation in which, for example, you fix the pressure or you increase the temperature. And so, in fact, if you do solve the equation of motion, the system is conservative, you move to on a surface of constant energy, which is a pretty unpractical situation from a technical point of view. So there was a seminal paper in the 80s. There was this idea, really, we were mentioning the fact of you need mathematics to tackle the problem. And the idea of Anderson, which was seminal, was to use this idea of extended Lagrangian. So it means that you take the Lagrangian of your system, but then you extend it to fictional or fake or particular degrees of freedom that you couple to your system in order to obtain the statistical ensemble that you want. So in particular, here you have the traditional Lagrangian, but now you're changing the volume of your system as if this was a dynamical variable. So you have a kinetic energy and so on. And so the idea behind that is that if you have a system now and the volume fluctuates, and you can fix the pressure as an extended variable, and this way you reproduce a constant pressure ensemble. But of course, if you do this for crystal, that's okay for a crystal like this, because of course, you expand the system, but you can find yourself in a situation in which changing the pressure will generate a change of the crystal, and this will mean that your box should be different. And of course, this is not possible in the classical Anderson result, because your isotropy is changing the shape of the box. So this was not possible. And I think this is where Parrinello entered the field of molecular dynamics in the 80s, when he moved to spend some time with Raman and developed his Parrinello-Raman scheme. And the idea is, well, simple to explain, nothing to think, but the idea is to make, in fact, your box flexible. I mean, now the box can change shape, can change angle, and all of this, you represent them as basic vectors, and you can write a matrix for this. The volume of this will be basically the determinant of this matrix that is represented by the vectors. And then you do the dynamic in this extended Lagrangian that now allows not only to change the volume, but also to change the shape. And so now all these are all tensor objects that represent this. And then you can write down from Lagrangian, you do the Hamiltonian equation. For with Hamiltonian formalism, you arrive to the equation of motion, and you have a equation of motion that you can solve. And now when you make a molecular dynamic simulation, you fix the pressure, you can vary the pressure, and now your system, this is from the original paper, you can see that your system can undergo a transition from distant crystal to one and another. So it was a very smart way of thinking about this extended Lagrangian to use them in different context. Like this was like a game changer, and it's used in a lot of situations. And one thing, I will speak very little about application, because otherwise probably we'll have to spend all the weekend talking about the application. But the application of this are huge, as testified by the number of simulations. But of course, you can have phase changes, but also you can also see how the system respond to a non-isotropic transformation. In fact, what I showed you before was an anisotropic compression. And so this is the Parrinello-Raman idea. So the next question I have is, how do we devise interaction potential in this kind of system, right? So we have this guy here. So one thing that you could do is to go with classical force field. So somehow you imagine that your energy is somehow is a two-body here, it could be larger, but at the end, a sum of a classical force potential. So the classical example is the Lennard-Jones potential, right? When somehow you have dispersion forces on this part here, this is a repulsive force. Or you can go even fancier. If you start to have molecules, you can have more complicated interaction potential, where you have bending, stretching, and all the possible angular. And this is a world that has been quite explored. And in fact, all of this, you have a lot of parameters to fit. And you generally, for atomistic simulation, you quantum mechanics calculation, and you fix the parameter. And now there are what is called force field, where all these number and parameters are contained. But of course, you see that in a lot of situations, this is a problem, right? Because if you really think about real quantum interaction, what I'm telling you is that in a classical force field, if you have a particle that moves inside to other particle, they just continue to interact as a Lennard-Jones. In reality, those at atomistic level, there are ions, they are the nuclei of the particle, and in fact, what you would have is that their electronic structure will interact with each other when they move. So you need to solve the electronic structure on the fly, or try to do that if you want to have really chemical description of your atoms. And so this has been mentioned before from Mariana before, the Born-Oppenheimer dynamics. This is textbook physics. The idea is that you have the Hamiltonian of the nuclei, the electrons, nuclei, or the interactions. But fortunately, you have a decoupling between the speed of the mass of the proton and the mass of the electron, so that basically the nuclei always move very slow and let the electrons relax in their state. And then basically what you can do, again, talked about a lot before, not an expert in the field, but the idea is that you get the density. You can use density functional theory, in which you can minimize this functional and have basically the electronic structure. And then the idea is that you can minimize, but then what you could do, you could use this minimization here to write down the dynamics, in which basically in each steps you minimize this density functional theory, and you evolve your dynamics as we did before. Of course, this is very complicated, because this minimization, especially at the time, was really, really expensive. And so Carr and Parrinello came out with a very nice idea that again goes back to the same principle of extending the Lagrangian. And so what they did, they took the Lagrangian of the system, where you have the electronic coupling, but now they took basically the wave function, the things in which is decomposed in function, and they give it basically a kinetic energy, and this is a Lagrangian multiplier to fix the normalization. And the idea is that you can write down the equation of motion of this guy, you can write down the force, and now your equation of motion, you have an equation of motion for the ions, an equation of motion that is a fictitious equation of motion for the electronic structure, and is dominated by this mass here, which basically tells you how you move. And it turns out that basically while you move the protons in your system, the nuclei in your system, the surface, what is called Born-Oppenheimer surface that evolves, it basically allows you to, if you write this mu small enough, instead of going always to the minima, you can wiggle around this minima here, and this is a Carr-Parrinello trajectory, and you can show that you can bound the distance from this Born-Oppenheimer with this mass. And then if you do that, it's much cheaper, because this is a regular dynamics, and you don't have expensive minimization, and in fact you have a good dynamic, because you have also an extended energy that is conserved. So if I show you, for example, this is a Carr-Parrinello, I think this is a solution from some silicon, and these are the exact Born-Oppenheimer calculation. You see no difference, and in fact, if you really plot the difference, you do see this oscillation there. And again, this has been a revolution in the field of computational physics and computational chemistry that is applied so much that, is one of the top 10 PRL paper. I think this was around 2000 that it chose the top 10 paper of this last century. And what was really amazed me is that it even create a Pax number. There is a Pax number between Carrier and sign and cars, which is a Parrinello method completely dedicated to that. I think it was in 96 that was. And so this was awarded for this result. Carr and Parrinello were awarded the Dirac medal. So Dirac comes again. And so this was of course, a big revolution in the field. So the next problem I want to explore with you is the problem of being trapped in phase space. And so of kinetics, basically, how do you move in this phase space? And so the idea is that if you think about your gamma space, so the position of all the particles, you are moving in a very complex energy surface. But often in chemistry or in application, you're not interested really in the whole behavior of all the position, but more of something that are called collective variables. That could be something that is a function of all the position, but represents something more physical in the system, right? Like, for example, you could imagine for a protein, a quantity that measures from B unfolded to B folded. And in fact, you can write down analytically, I mean, you can derive and have an idea of what the free energy of this object here. And what happens often is that you can have a different reduced space in which you have these different minima, and your system moves between these minima. And in fact, this variable here now they have interesting properties from the point of view of the physics or the chemistry that you're interested in. And so everything seems fine, but you end up with a problem, is that the probability of being in a certain place is proportional to this e to the minus beta, is an activated process. And of course, what you can have that your reactant and products have a jump of energy between them that basically you cannot pass. So you end up stuck in one of the two sides, but you would like in statistical in your simulation to explore all the possible configuration and goes from here to here. And so I mean I did a little simulation into D. That's the situation, right? So in a situation like this, in which you get a little bit of energy, you get stuck in this minima, whereas you would like to go up and forth and maybe even, and this will allow you to maybe have the idea of what is barrier here. And then the idea that they had, Laio and Parrinello in 2002, was for me super brilliant. And the idea was very simple. If you can think about like a bucket when you are a kid, and imagine you want to know the shape of this bucket. What you do, you fill it with sand, you put it down, you take it up, and you have the shape of the castle, right? And so they basically did the same with the simulation. And the idea is you start from your system. This is your system, and now you create a time-dependent bias that is basically your particle, your system, in moving in this coordinate space will leave a Gaussian every now and then, slowly filling the space. And then eventually, so this is the biased Hamiltonian, so you run the dynamics of this Hamiltonian. So when you do that, that's what you have now, yes, an energy potential, you start to move, and what you see is that your minima start to fill up, and now your particle can go everywhere, and now you can measure, in fact, the accumulated bias potential, right? And you probably see it's very similar to this guy. In fact, in the first approximation that the method was refined, is that in fact the free energy you look is really like minus the potential that you have accumulated. And if I take the results before, these are simulation I ran in Langemann dynamics, you get exactly the free energy you had. So for me, it was very, very smart and very cute, beautiful results and idea. And so this has been used again for so many different applications that I will not list it. And the amount of paper citing this work has been growing steadily. And again, this has mentioned it before. I think this has one of the things that Michele Parrinello was very important was to promote the creation of tools that the community use. And now PluMed becomes one of the reference to do molecular dynamics with metadynamics. The last question is how to bridge a gap between basically atom and molecules and large systems. So again, there is a problem we haven't solved, which is a problem of how you have a very costly quantum mechanics dynamics, but you need a lot of atoms for a lot of properties. So how can you bridge that? So it has been touched quite a lot from the talks before. And the idea, I mean, the naive idea would be you take the FT results, you get the energy landscape, you make a fit, and you get the potential. Of course, this is super naive and was not possible until we developed basically a neural network representation, which are very smart way of fitting very complex object, multivariate objects. And so the idea would have been to do DFT, then make the potential landscape, and now decide to do a training, which is nothing less than a fit, and having a potential that is a neural network potential. In fact, this idea was explored first in the 90s. I think this was a very simple model in which there was an atom moving on a surface, which was was an interesting idea, but was quite limited because you would have as an input layer, so what you feed your neural network with only two variables. And the idea there was that, okay, you have to generalize this to all the position of all the atoms. It's too much, right? And you cannot really get by. And so then in 2007, this was already mentioned, Beller and Parrinello had this very smart idea of devising a neural network in a completely different way that is inspired with what you know about physics. This is what I like about this. There's always physics in all these results. And the physics of the project was like, I start from the position of all the particles, and now instead of feeding them to a network like a black box, I think and I know that basically in a condensed matter system, an atom feels mainly what happens around him. And so instead of passing through the position, I pass to something that are descriptors. And I use the descriptors to train a neural network that measure the energy of the single atom. And then I sum all of them and I get the final energy. And so this descriptor, now I can use what I know are local structure and are basically combination of how many neighbors I have, and now they are oriented in the original idea. And I mean, this looks objects that looks like this, that basically count how many particles there are. But when you do that, now you have reduced and you really have informed and trained your network with something that contains much more. You have distilled yourself with your knowledge of the physics of the problem. And when you do this, you get very nice results. And this is the deviation from the accuracy. And this was the first paper, as it was mentioned before, that boosted all the work on neural network machine learning potential that is now exploding because, of course, the applications are numerous. And this is basically the general approach to this kind of system. And you always see that there is always a moment in which you put down a descriptor, right? A descriptor of the system. And this is what they sort of came with and that make the system boom in such a way. And of course, this is incredible. And of course, I mean, we thought about this problem of different length scale. And what I find incredible is that if you look now at the time scales of a traditional system, we are somewhere here, but you see this is the error with respect to a DFT calculation. But of course, it's faster, right? But now you see that with ML potentials, you are basically at the same. So you gain like 6 orders of magnitude and the error is much reduced. So you can only imagine how much, because one of the big problems of machine learning, of molecular dynamics is that you can make the system big by parallelizing, but the time is always a bottleneck, And here, 6 orders of magnitude. And this is really a field that is going on its own. So I told you one application, and what I like, I picked one in which there are all of these things together, and it dates like, I think, last year, something like this, 23 or 22, maybe I don't put. And the idea is about gallium. And so gallium had distant structure, so you have to use Parrinello to predict them. It has very difficult potential, so you learn it by neural network. And finally, you have to overcome barriers, and then you use metadynamics. And when you do this, you find the transition between the different states, and you find a phase diagram that is really close to the one of the experiments. And my last application, which I think is something that Michele will talk a bit about later, is something very recent, 2024, is the idea of using machine learning to learn about transition sampling ensemble. And the idea is that in this kind of surface where you have reactive coordinates and two minima, the holy grail is to go, of course, now we know how to go from A and B, we know how to calculate the rates maybe with metadynamics, but what we don't know is really what happened around the bottleneck between these two valleys. And this is very important because you want to know a bit when you pass from one state to another, what are really the transition states that are on the top of the valley before you feel here. And in this paper, they developed this idea of a committer is a probabilistic object. I mean, they don't develop, they use this concept of committer. It's basically the probability that if I start from a point here, I will fall in B with never falling in A. And the idea is that this function here is 0 here, of course in A, you will not fill in B, and it's 1 here, right? So it's a very flat function here and here, but of course it's different from 0 in between the two. And so if you take the derivative of the guy, will give a big contribution there. And so the brilliant idea was say, okay, let's bias the system with a potential that somehow will get attractive there. And we'll drag the things here. And of course, it's a bit, I like in the paper, he say the chicken and the egg. I think it's a chicken and the egg problem because you bias the system with something you don't know. And then they develop a method which is complicated and super, I mean, it's an iterative method, but the idea is that you bias your system with this potential. If you knew this potential, that means that this is your original potential surface. You bias with this potential here, which is quite negative, right? Well, it's like really made like this. You sum them, and now you are attracted here and here. And now you need a way to do this, and you do this with machine learning and neural networks. And basically, after several iterations, so this was the original system, you find the barrier between them, which is really when the transition here, this is where the committer will be equal to 1/2. And also, most importantly, you find the states around the committer. Which is really what you want to see. You want to see what happened. And in a more, so these are this transition state ensemble. And so in the paper, there is this reaction between this reactant and this product. And basically, they found that most of what is in the middle, really that is what brings you there, are two specific conformations that really live in these things. And this, for me, was a fantastic achievement. So another thing that I think it really impressed me, because I was for a long time in Switzerland, is like the big community. This is stopping, but it could spin all the time. But the big community of people Michele Parrinello I interacted with. And you can see them here. I think this was this September. And from all years, right? And all of them, they built their own career in different methods. And Michele Parrinello has been like a bit of an ion in the middle of this cloud of brilliant people. And so with this, I'm about to finish. So the question was what Baldad would have done with a computer. And I hope that we know what Michele Parrinello is doing with a computer. Is doing, because as you know, is still hyperactive. And so it was for me a great pleasure to introduce you.
Thank you, Giuseppe, for a wonderful laudatio. You had an impossible job,
oh my God.
Fitting all the achievements of Michele Parrinello in half an hour, but you succeeded wonderfully. You succeeded wonderfully. Thank you very much for that. And by the way, this picture of Boltzmann on the computer was produced without the use of AI, right?
Also this one. I see, use all the technology, Google.
That's right. So thank you very much for that.